Hello everyone and welcome to today's lecture. Today we'll be talking about various properties that are useful when computing integrals, double integrals. We'll also talk about certain applications and theorems that extend from single variable calculus to multivariable calculus, which are very useful as well, such as the mean value theorem, and then also the idea of solving for, say, a given value by using, such as volume or area of a function, using the double integral. We've already seen this for rectangular domains, but we'll see that we can even set up double integrals for non-rectangular domains as well. So let's start off by listing some of the four basic properties that we can always apply when integrating. And we'll just remember here that for each one of these properties, we'll be talking about, say, the integral of one and possibly two functions. So we'll have two functions, f of xy, g of xy, of two variables that are integrable, or Riemann integrable, so we can do the Riemann integral of both of f and g. And we'll be integrating over a domain, we'll call it R. In two-dimensional space. So we'll be considering properties of the double integral over some region R. So the first property, and a property that we saw in some of the examples gone over in the previous lecture, is that what happens when you take the double integral of any constant c. So suppose c is a constant real number, and we take the double integral over the region R of a function f of xy dA. This is the same thing as that constant c times the double integral of f. So we can pull constants out of the integration process, just like we can in single variable calculus. The idea behind this is very, very, if you want to say prove this or show this, we'll do a justification. Well, the Riemann sum for this function, c times f of xy, is just going to be of the form, it'll be a summation from, double summation from I equals 1 to n, and then j equals 1 to n, of c times the sample point, so it's c times the function at the sample point, times delta aij. And because this is a summation of multiple different values from the summation rules from a previous calculus course, and also you can think of just, algebraically, if you do c times a plus c times b, this will always be equal to c times a plus b for any finite sum. So this sum is going to be the same thing as c times the double summation over I and j of the function at the sample point times delta aij, which is the Riemann sum for the integral of the function f. This is a nice justification of why the constant rule holds. So this tells us directly then that the constant rule is telling us that if you take the integral of any constant times a function, it's the same thing as that constant times that double integral. We have the sum and difference rules, which are also very, very similar. It says that we take the double integral over some region R of f of xy plus or minus some function g of xy. The sum difference rules tell us that this improper integral, or this integral, is going to be the same thing as the sum or difference of the first function with the second function, the integral of the second function. This is both over R. This is very, very useful. It says that if you have two functions, the sum or difference of a number of different functions, you can actually just consider each one individually and do each one individually. So again, this rule is very, very similar to the rule for single variable integrals. Not only that, the justification again is similar. I won't go through the justification for every one of these, but I can assure you that all of these justifications are done using Riemann sums, very similar to how we did the first justification for each of these properties. This is the second major property for integrals. The next property is called the domination property. And this says that if a function, say f, is always greater than or equal to another function for points in the region R, then necessarily the double integral of the top function must also be greater than or equal to the bottom function. For points in R. And this also kind of gives us a justification before for saying that, well, if a function is positive, so greater than or equal to 0, then the double integral of that function will also be positive over the region R. You can double integral of it, and it shows you that that exact value can be thought of as a volume. It's the exact volume under the graph of the function f of xy, which is very cool. And the last property that we have, again, all of these properties are directly from analogous properties for 1D functions, but they also hold for multivariable functions as well, which is nice. So the final property is called additivity. And this says that if our domain R can be split up into multiple different parts, which any domain can, say we have our domain R, and this is, say, split up into two separate subdomains, R1 and R2. The additivity property says that the double integral of the function over R is in fact equal to the double integral of the function over R1 plus the double integral of the function over R2. This is analogous to how in 1D calculus, in single variable calculus, for any interval from A to B, if you split it up into a two parts, or any number of parts really, and you integrate the function from A to B, the integral from a to b of the function is the integral from a to c of the function plus the integral from c to b of the function. Right, so that's what this additivity property is saying. It's directly generalizing this property, the additivity property for single variable integrals. But it's very, very powerful for us because what it allows us to do is take very complicated domains and just compute the double integral over those domains by adding the double integral over simpler pieces and simpler portions of the domain. So these are the four basic properties that we have for the double integral, and it really helps us go through and calculate the double integral on any domain we wish to consider. So I would call these the most basic properties of the double integral because they're used most frequently in terms of going through and simplifying calculation procedures for the double integral. But we'll look at some more advanced properties now as well. And in order to do that, we first need to go through and define what it means to take the average value of a function. Because this is going to be intimately related with what's called the mean value theorem for double integrals. So you'll hopefully recall that in 1D, for a single variable function, the average value of a function is defined as follows. If you have a function on some interval from a to b, and we define the average value of the function on that interval to be the accumulation of the function on the interval divided by the size of the interval. And so both of these things can be calculated directly. The accumulation of the function on the interval is the integral, definite integral from a to b of the function on the interval. And the size of the interval is just the length of the interval, or b minus a. So this is the main formula that we have for the average value of a function. Computing this value will give you a number, and that number is exactly the average value of the function on that interval. Using this idea, we can go through and prove, using the fundamental theorem of calculus, what's called the mean value theorem. Which states that for a continuous function on an open interval, that there exists for a continuous function f, there exists a point, at least one point, I'll put in parentheses possibly more, for which the value of the function is equal to the average value of the function. So let's say we have that point. You can go through and solve for that point if you have the average value, and we'll say that. So this means that, so we'll call this point xi. So this means that at this point, the value of the function at xi is equal to the average value of the function, or the integral or accumulation of the function divided by the size of the interval. We can rewrite this a little bit by saying this is the same equation as saying that at this point, the integral of the function from a to b is equal to f of xi, which is that special point, times b minus a. And so this is guaranteed for us that there exists some point xi that satisfies this equation. Going through and solving for xi sometimes is a tricky procedure, but we're guaranteed the existence of this point from the mean value theorem. And so what that means then is that we can actually always bound the integral from a to b. So if this is true, if this is equal to at some point the definite integral of the function, and we need a dx there as well to be consistent with our integral notation. So if at some point the integral from a to b of the function is equal to the function at some point times b minus a, well, that value of the function, f of xi, will always be bounded above and bounded below by the maximum value of the function over the interval from a to b, and it's bounded below by the minimum value of the function from a to b. So this improper integral then, or this not improper integral, this integral will always be bounded between the maximum value of the function on the interval from a to b times the length of the interval and the size of the interval, and it'll always be bounded below by the minimum value of the function on the interval from a to b times the length of the interval. So this is kind of a powerful result. It says that for any function, continuous function on any closed interval from a to b, we can always do this procedure and figure out what the total maximum is, the maximum possible value for the interval is, and what the minimum possible value for the integral is as well. We have an upper and lower bound, which is very, very useful in many, many applications. But the idea here is that this is kind of a review of the 1D mean value theorem and the 1D average value formula from single variable calculus, so Calc 2 course. As it turns out, which is a very common theme in multivariable calculus, is this can be directly generalized to double integrals, and also we'll see to triple integrals a little bit down the line. So this idea of average value and the mean value theorem are directly extendable to functions of two variables for the double integral. So we'll go through and figure out first what the average value of a function of two variables is going to be. and then go through and state the mean value theorem for this. This is average value of a function f of xy on some region R. So just like in 2D, we have some function, and this function is, say, or just like in 1D, this function is defined over some region R. And let's say we want to find out what the average value of this function is on this region R. Well, this average value, again, we want to think of it as the accumulation, total accumulation of the function in the region R divided by the total size of the region R. Both of which we can actually evaluate, which is very, very nice, using the double integral. Specifically, the average value of f is going to be equal to the accumulation of the function is just the double integral of the function over the region R, and the size of a two-dimensional region is going to be the area of that region, or as we showed last lecture, just the double integral of the constant function 1 over that region. For rectangular regions, that area is relatively easy to calculate, but be careful because in general, for a general region R, we don't know that it's rectangular, so you might have to go through, when you're calculating the average value, and in general compute two integrals. You'll have to do an integral procedure for the numerator there, and the integral procedure for the denominator as well. So please be very careful when you're going through and doing that, right? Not all regions are rectangular. You have many different, more complicated regions. So this formula is more complicated if you have a more complicated region, which in general is true for the double integral and the triple integral. But using this idea, we can directly state the mean value theorem for functions of two variables. And it is very, very similar to the 1D case. It says that let f be a continuous function of two variables on some region R. This is saying, the mean value theorem directly is saying that there exists at least one point possibly more, such that the value of the function at the point is equal to the average value of the function over R. So we'll call this point, for notation, xi comma eta. They're two Greek values. So the x-coordinate is xi of this point, and the y-coordinate is eta. So what the mean value theorem is telling us is that the value of the function then at xi comma eta is equal to the average value of the function, or the double integral over r of the function, divided by the total area of the region R. So this is the same thing as saying, if you multiply by the double integral of the function 1, or the area of the region R, it's the same thing as saying that the double integral over R is equal to this f of xi eta multiplied by double integral of 1, or the area of the region R. And because this function f will always be bounded between its maximum and minimum values, so we'll call the maximum value of f m over r, and the minimum value lowercase m. This equation is telling us that the double integral of any function over any continuous function over any region R will always be bounded above and below by the maximum value of the function times the area of the region R, the double integral of 1, and it'll always be bounded below by the minimum of the function times the double integral of the constant function 1, or the area of the region. So this is the direct extension, right, of the mean value theorem for a single variable function, but it turns out that it also works for a multivariable function as well, and it's very, very important. It's a very general result. Proving it is not straightforward, takes a little bit of work, but the idea here is that it's directly applicable to many different scenarios that you might want to consider if you don't know how to evaluate an integral. So you can use this in a very powerful manner to figure out the correct bounds for an integral. So we'll consider the following example and show that we can directly do this and apply this theorem. Specifically, we'll consider applying this theorem to the function f of xy, which we'll take as the polynomial x cubed minus 3x minus 1 times y squared on the rectangular domain from -2 to 2 in x and -2 to 2 in y. And the first thing we have to do to apply the average value formula is to figure out the integral of this function on this region. So let's go through and do that. The double integral over r of this function is going to be the iterated integral from -2 to 2 of x cubed minus 3 times x minus 1 times y squared and this is evaluated by doing the inner iterated integral first. So the antiderivative of this function with respect to y is going to be x cubed times y minus 3 times x minus 1 times y cubed over 3, which is just x minus 1 times y cubed. This is evaluated from 2 to -2 from the fundamental theorem of calculus for single variable functions. this integral now, when we plug in, will be the integral from -2 to 2 of x cubed times 2 minus x minus 1 times 2 cubed minus x cubed times -2 minus x minus 1 times -2 cubed, which simplifies to the integral from -2 to 2 of 4 times x cubed minus 16 times x minus 1. This will be equal to the antiderivative of this function with respect to x, which will be x to the 4th, 4 times x to the 4th over 4, which is just x to the 4th, minus 16x squared over 2, which will be 8 times x squared, minus 16 times x times -1, which is plus 16 times x, evaluated from -2 to -2. So our final value will be 2 minus 8 times 2 squared plus 16 times 2 minus -2 to the 4th. Oh, and this should be 2 to the 4th right here because we're plugging into this guy right here. Minus 8 times -2 squared plus 16 times -2. And when we go through and simplify this, 2 to the 4th minus -2 to the 4th is 0. 16 times, well, we have this -8 times 2 squared minus -8 times -2 squared, which will be 0 as well. And then lastly we have 16 times 2 minus -16 times 2, which is going to be 16 times 4. So our final value for this integral is 64. So this, the integral of this function over the rectangular domain from -2 to -2 is exactly just equal to 64. Which means that the average value of this function on this interval is going to be the integral of the, on this domain is going to be the integral, double integral of the function over r, which we just calculated, divided by the area of r, or the double integral of the constant function 1. Now, this will always simplify down to just the area of a rectangle for rectangular domains only, but because we have a rectangular domain, we know that this is going to be exactly equal to 4 times 4. So the average value of this function is going to be the accumulation of the function, which we found before to be 64, divided by the area of the region, which I recommend going through and showing that it'll just be 4 times 4, but this will always be the case for a rectangular interval, that it's just the width of the base times the width of the height, times the length of the height. This is going to be 64 over 16, or 4. So the average value of this function of f on this domain we've calculated to be equal to 4. Now what this means is that the mean value theorem guarantees at least one point, possibly more, such that the value of the function at that point is equal to this average value. So any point that satisfies the value of the function equal to 4 is satisfying the mean value theorem. So what this is showing us is that, right, this is a lot of points. There's actually infinitely many points. Any points on the level curve of the function that correspond to the level 4, are satisfying the mean value theorem, because the value of the function at that point is equal to the mean value or average value of the function. This is best seen by visualization. So what we're going to do is show a level curve plot of this function and show exactly where this is for this function right here. So let's open up Desmos and do that. I already entered all of the Desmos functions in, so we can see this immediately when we open up this plot. So here you can see all of the level curves of this function, and I'll go through right now and explain the mean value theorem in its application here, and you can hopefully see this in this already. But so we'll go through and explain the level curve plots here. So this solid line right here, it's a black solid line, as well as this solid line right here, and this solid line right here correspond to the function being equal to 0. The dotted lines, the dotted curves I should say, correspond to negative values of the functions. This is -1, -2, -3, and so on and so forth. Same thing right here and right here as well for these dotted lines. Those correspond to negative values of the function. The other solid lines, which are red, correspond to positive values of the function. So this line right here, or this curve right here, corresponds to the value of 1. This one corresponds to the value of 2. This one corresponds to the value of 3, and so on and so forth. So the function is increasing in this direction, increasing in this direction, increasing in this direction, decreasing in this direction, decreasing in this direction, and decreasing in this direction. The last line that's of interest is the dashed line, which is a green line. And that line is the level curve of this function corresponding to the value of the function being equal to 4. And what we've shown is that this any point on this line is the function value is equal to the average value of the function on this domain, which is satisfying the mean value theorem. Because any point here on this curve, the dashed curve, is satisfying that its function value at that point is 4, which is the average value of the function. Therefore, it satisfies the mean value theorem. And you can kind of see that it's kind of in between, the average of this function. It makes sense that it's 4 because there's definitely more regions here where you have a more positive value of the function than a negative value of the function. This is a very nice example showing directly, the application of the mean value theorem to an actual example function. So we've seen a number of different examples of integrals over rectangular regions now, and what we want to do is develop a procedure for integrating over more general regions in Cartesian coordinates. So this is what we're going to talk about now. So the idea is we want to answer the question, how do we go through and integrate over non-rectangular regions? Or how to find the definite integral over more general non-rectangular regions. And the idea here is that you always want to draw a picture and consider how to decompose our region into what are called simple domains. The idea here being that a domain is simple if so we have a rectangular region R, or a non-rectangular region R, and it looks like the following. Picture right here, where it looks like it's going from A here in X to B here in Y. And the idea here is that we say this is a simple region R when the upper bound and the lower bound can be expressed as a simple function of x. In this case, this upper boundary of this region is this red curve. We'll say y is equal to h of x. And the lower boundary is this green curve, or this blue curve, sorry. Y is equal to g of x. So we say then that the double integral over this region, or the double integral of, say, a given function, f of xy, on this region, the double integral of f of xy dA is going to be equal to double integral, and if it's simple with respect to x, so the upper bound is a function of x and the lower bound is a function of y, this integral is going to be the integral from a to b in x, so x will be our outer variable of integration, and then that means that y will be our inner variable of integration. In the bounds, right, you can think of as like sliding a point across for any value, fixed value of x. The lower bound is given by this point right here. In the upper bound, the blue on this blue curve, y equals g of x. It's the lower boundary, and then the upper bound is given by this point right here, which is y equals h of x. So over this domain, right, this cross section of the domain corresponds to this value x. If you say go to a new value x, 1, say, this is the lower bound at this point, this is the upper bound at this point, and you can think of sliding this point x1 or any other point x all the way across this domain to capture the entire domain. So that means that in our integral, our iterated integral, if we're going from a to b in x, then y is going to be going to from the function g of x to the function h of x. And then we're still integrating the function f of xy. And this is the idea for doing the integral over a simple domain. This is a simple domain in x. Now, if say you have you want to do the opposite integral or the opposite direction, you'll actually do that, and this is related to Fubini's theorem. So I'll discuss how to switch the bounds in the next lecture. So lecture 17. But the idea here is that for now, let's just go through and see some examples of getting the integral using this idea. We want to see a couple of different examples of this. So before I show an example of this, what I want to do is kind of just demonstrate this, that I've shown a general, possible simple domain here. The general picture that I drew before is a little bit more general, but the idea here is that really, as long as you can describe the top boundary and the bottom boundary by a function of, in this case, if it's simple with respect to x, it'll be a function of x. If it's a function with respect to y, then it would be a simple domain with respect to y. But this is a simple domain with respect to x, and as we go through and integrate, right, at every given point value of x, we're going to have a different lower bound and upper bound. The upper bound and lower bound are changing, which is why we have to put the correct upper bound and lower bound in as functions of x. And you can very clearly see that in this region, the upper bound and lower bound are changing. So this is why we have to include them as functions in the bounds of integration. If you don't do this, the value of the integral is not going to come out correct. So for instance, for the y bounds in this general integral, if you just put in, on this domain, you're going for x from -1 to 1, and the correct y bounds are from this function, the lower bound, to this function right here, which is the upper bound. If instead you put in from -1 to 1 for y, you're going to get the integral over the entire rectangle, which is not what we want if we're only considering the integral over this non-rectangular region. So this is the reason why we have to do this, and you have to be very careful for general domains. You don't want to accidentally integrate over a rectangular region. Lastly, I also want to point out, before we get into the examples, that if in fact your region is not simple, that's okay. Right? You can rewrite the region to be a union of simple regions. So for instance, if we have a region that we want to integrate over, that looks like this, say, this is our region that we want the integral of. This is a non-simple region. However, we know by additivity that we can cut this up and the correct integral, right, over this region R will be the same thing as the sum of the integral over R1 plus the integral over R2 plus the integral over R3 plus the integral over R4 plus the integral over R5. Right, so the general region R here is the union of these 4 subdivisions, each one of which is a simple region. So we can evaluate the integral over R1, the integral over R2, R3, R4, and R5, and then just add these values together. So this is a very important idea, and it's very, very important when going through and doing this. So really all we need to consider is simple regions like this. So let's see an example.